Hello, welcome to my video series of algorithms. This is part 3 of Module 2, Logic and Proof. In this video, we'll discuss logical connectives. In the previous video, we have discussed propositions or statements. We know that propositions and statements are sentences whose truth values can be unambiguously determined. A proposition or statement can be a simple sentence or be constructed from a predicate. We can either provide specific values for the parameters of the predicate or quantify the parameters using quantifiers. Now, once we have the simple statements, we may want to express meanings that involve the relation among multiple statements. In this case, we use logical connectives to indicate the relation among multiple simple statements and then combine them into a more sophisticated statement with a richer meaning. The combined statement is called a compound statement. Note that a compound statement is also a genuine statement. It means that it also has an ambiguous truth value. In this video, we will introduce the basic logical connectives and ways to determine the truth value of the corresponding compound statements. We can also think of a logical connective as an operator such as addition or subtraction, which transforms its operand into a result. For example, the addition operator takes two real numbers as its operands and outputs another real number. Similarly, a logical connective takes in one or multiple statements as its operands and outputs another statement as its result. Again, the resulting compound statements have their unambiguous truth values, just like other simple statements. We will introduce 6 logical connectives in this video. They are the conjunction or the AND connective, the disjunction or connective, and the negation or NOT connective. We further have the exclusion or XOR connective, the implication or the if connective, and the double implication or the if and only if connective. Below, we'll discuss them one by one. First, we have the conjunction or AND connective. It takes two statements as its operands. The corresponding statement says that both of the connected elementary statements are true at the same time. For example, let P denote today is sunny, and let Q denote I played soccer today. By using a conjunction connective, we get P and Q, which means today is sunny and I played soccer. Here, the statement P, today is sunny, is an elementary statement, so as Q. The connected statement, today is sunny and I played soccer, is the compound statement. Note that the resulting statement thus have an unambiguous truth value, which can be determined based on the two elementary statements. That is, whether the statement P and Q is true depends on whether P is true and Q is true. We have the following rule to determine the truth value of a conjunction compound statement. The compound statement is true when both elementary statements are true, and is false when either one of the elementary statements is false. The truth value determination rule is summarized based on the definition of the corresponding connective. Therefore, we need to memorize the rules. The truth value determination rule can also be summarized into a truth table, which is a breakdown of all possible truth values returned by a logical expression. You can see that the logical expression here is P and Q, and that we have considered all combinations of the truth values for P and Q to enumerate all possible outcomes. You can see from the first row of the truth table that when P is true and Q is true, the corresponding truth value for the compound statement P and Q is true. For the other cases, the truth values of the compound statement are all false. This is consistent with the original description of the truth value determination rule. With the truth table, we can look up the truth value of a compound statement using the truth values of its elementary statements. For the previous example, if we know P is true and Q is true, we will refer to the first row of the truth table and find that the corresponding truth value for the compound statement is true. If P is true and Q is false, then we'll refer to the second row and find that the corresponding compound statement is false. Let's look at the second logical connective, the disjunction or connective. It connects two elementary statements. The corresponding compound statement says that either one of its elementary statements is true. For example, denote P as I drink tea in the morning, and denote Q as I drink coffee in the morning. The disjunction compound statement P or Q says I drink either tea or coffee in the morning. A disjunction statement is true when at least one of its elementary statements is true, and is false when both of the elementary statements are false. The corresponding truth table is shown here. The third connective is the negation or not connective. It takes only one operand or elementary statement. It states that the opposite of the elementary statement is true. For example, let P be this car can accelerate to 100 kilometers per hour in 6 seconds. The negation statement becomes this car cannot accelerate to 100 kilometers per hour in 6 seconds. A negation statement is true when the elementary statement is false, and false otherwise. The corresponding truth table is listed here. The fourth connective is the exclusion or XOR connective. It takes two operands or elementary statements. It says that the two elementary statements are exclusive or have different truth values. For example, denote P as Tom works on the project. Denote Q as Jerry works on the project. The compound statement P XOR Q says either Tom or Jerry works on the project, but they don't work on the project together. The exclusive statement is true if both of its elementary statements have different truth values, and false otherwise. You can also find the corresponding truth table here. The fifth connective is the implication or if connective. It takes two operands or elementary statements. The two elementary statements are ordered. The former statement is called the condition, and the latter is called the conclusion. It states that the condition implies the conclusion. For example, denote condition P as there exists someone in the class wearing a jacket. Note that this statement is constructed from quantifying a predicate. We also denote the conclusion Q as the weather is below 50 degrees. The corresponding implication statement P implies Q means if there exists someone in the class wearing a jacket, then the weather is below 50 degrees. The implication statement is false only when the condition is true and the conclusion is false. The corresponding truth table is shown here. Note that the third and the fourth rows of the truth table, which says that when the condition is false, the implication statement is true, disregarding the truth value of the conclusion. This definition is a bit counterintuitive. The explanation is that when the condition is false, we have not satisfied the requirement for the conclusion to happen. Therefore, no matter whether the conclusion happens or not, we cannot say the implication itself is false. Hence, the corresponding truth value for the implication statement is true. The sixth connective is the double implication or if and only if connective. It takes two operands or elementary statements. It says that the two elementary statements are equivalent and have the same truth value. For example, denote P as x is larger than 0, and denote Q as x is a positive number. The corresponding double implication, P if and only if Q, states that x is larger than 0 is equivalent to x is a positive number. A double implication statement is true when its two elementary statements have the same truth value, and false otherwise. Here we have the truth table for the double implication connective. Now we have introduced 6 logical connectives so far. Then I would like to discuss how to construct more complicated compound statements by recursively applying the connectives. For example, denote P as today is Thursday, denote Q as I go play tennis, and R as today is sunny. We can first construct a compound statement, P and R, which says today is Thursday and sunny. Note that the compound statement is also a genuine statement. In this case, it can serve as an operand for another connective. Say we use this compound statement as the condition of an implication connective, and use Q as the conclusion. Now, we have a more complicated compound statement that involves 2 connectives. The resulting statement says that if today is Thursday and sunny, I will go play tennis. To determine the truth value, we will recursively apply the truth value determination rules. First, we construct an empty truth table. Since we have 3 elementary statements, P, Q, and R, we need 8 columns to enumerate all of their truth value combinations. Then, we will add 2 auxiliary columns for the intermediate results. We add columns for P and R, and P and R implies Q. First, we will fill in all combinations of P, Q, and R's truth values. Then, we will compute the truth values for P and R using the truth values for P and the truth values for R. Now, we can compute the truth values for P and R implies Q using the truth values for Q and the truth values for P and R. For more complicated compound statements, we can apply the above process recursively to determine the truth values. Lastly, I want to clarify that some of the connectives are essential and some are redundant. It means that the redundant connectives can be constructed from the essential connectives. In some literatures, conjunction, disjunction, and negation are considered as essential. In some other literatures, implication and double implication are also considered as essential. It means that the exclusion connective is a redundant connective, and its logic can be constructed from the other logic connectives. I would also like to clarify that exclusion is not the only redundant connective. There are many more of them. You can read more specialized materials in logic to find out, if interested. Let's see how we can generate a redundant connective using essential connectives. Let's try constructing implication using negation and conjunction. We say P implies Q has the same meaning as not P and not Q. This is because we know for an implication statement, the only scenario that is false is when P is true and Q is false. In this case, we will add a negation to P and not Q and make it true. Next, we will need to show that P implies Q indeed has the same meaning as not P and not Q. We will prove it by showing that these 2 statements will always have the same truth values for each combination of the truth values of P and Q. This can be done easily by constructing and comparing the truth tables for the 2 statements. We begin the process by copying the truth table for the implication connective. Then, we will construct the truth table for the second statement, not P and not Q. We first write the intermediate statements as auxiliary columns. It will make the truth table construction process easier. We need 3 more columns for not P, P and not Q, and not P and not Q. We will first fill up the column not Q using the truth values in the column Q. Then we will compute P and not Q using P and not Q. At last, we can compute not P and not Q using P and not Q. Now, we can compare the 2 columns for P implies Q and not P and not Q. We can see their truth values are identical for each row. Therefore, the 2 statements have the same meaning. We also say that these 2 statements bear logical equivalence. We will discuss more about logical equivalence in the next video. Using the same process, we can express the exclusion connective using conjunction, disjunction, and negation. You can verify the result by yourself if interested. In summary, we have introduced the notion of logical connectives. Using connectives, we can express the relation among multiple elementary statements and construct complicated compound statements. We introduced the meaning of 6 common connectives and the rules to determine the truth values of their corresponding compound statements. We also show that we can recursively apply the connectives to build more complicated compound statements, as well as the way to determine the truth values of these compound statements. Finally, we introduced the notion of essential and redundant connectives and gave 2 examples of how to construct redundant connectives using essential connectives. In the next video, we will discuss more about logical equivalence. Thank you for watching and see you next time.